Our publication, the Quantum Convolutional Neural Network based online malware file detection for smart grid devices, was supported by my colleagues in the Cyber Physical Power and Energy Systems Laboratory and was presented by Dr. Taisik Kim in Miami, Florida. This here presents a slight overview of our published paper, which includes the introduction, where we talk about our problem statement, includes the related work section, where we provide knowledge on smart inverters and DER systems, and lastly, the related works also includes quantum computing systems and how quantum computing systems can aid machine learning. The section 3 is the proposed quantum CNN based online malware file detection system, where we clearly describe the data collection and pre-processing techniques for the machine learning model, the quantum CNN architecture, and how we used deep transfer learning to train the quantum CNN. Lastly, we end our presentation with validation results of our machine learning model and a conclusion. The introduction shows our problem statement where smart inverters, especially grid connected inverters, can be vulnerable to ransomware. As seen on the top right of the slide, of a present and a futuristic model of distributed energy resource systems can be seen, whereas in the future one we see the use of more inverters as the need for DC power systems increase. Additionally, in recent years, the Quanti ransomware attack, the SolarWinds attack have proven very, very critical for such infrastructure which is connected to the grid. The first section of the related works shows Texas A&M University Kingsville's previous work and previous research test benches, as seen on the top right, and how PV systems, especially smart inverters, are vulnerable to ransomware attacks. The second section introduces quantum computing and quantum machine learning using the visual representations as shown in the slide. Mainly two types of quantum technologies are available for commercial use at the moment, which include quantum annealing and gate-based models. Annealing, where annealing is more of a combinatorial solver or an optimization problem solver. Gate-based models assist in feature extraction and to solve differential equations. The last section of related works gives us a deep dive into quantum machine learning algorithms and how they can be formulated. As seen in the left, complex machine learning systems that involve the use of quantum computing can be of two types: a gate-based quantum computing system or an adiabatic quantum computing system, which is essentially a annealing-based quantum computing system. As you can see, the difference between the two can be very evident, as gate-based models use quantum circuits to encode and process the data, whereas adiabatic quantum computing encodes using the Cubo formulation, and there is an extra embedding step before we can send our data to the quantum annealer. On the left, we try to show Texas A&M University Kingsville's previous work on quantum annealing-based machine learning, where with admirable amount of accuracy, we got a very robust algorithm which has less contributions to adversarial attacks. In section 3, just like we previously mentioned, we described the proposed quantum CNN network that we are using for the online malware detection. As you can see, the main goals for this research was to perform binary analysis to malware files, to explore the capabilities of quantum machine learning, especially quantum CNN, when it comes to static malware analysis. The main stages of the pipeline include data collection, data preprocessing, quantum data encoding. Just like I mentioned previously, in gate-based algorithms, we need quantum data encoding. Lastly, feature extraction and deep transfer learning training. Just like every machine learning model, At the end, we test and deploy our machine learning model in appropriate systems. The data collection and pre-processing is a technique that we've been using for a long time throughout various publications, and it is a very famous technique to convert binary values into images, and it has been studied widely in static malware analysis. And the only reason we perform this kind of static malware analysis is because, regardless of the vendor, every firmware file, maybe it's an exe file, maybe it's a .bin file, depending on the OS the inverter is operating in, but the inverter files can differ from time to time. But using a binary static analysis, we can, regardless of the manufacturer, regardless of the type of file, we can always gain similar patterns when we turn them into images. After the data collection is done, we provide simple pre-processing, which involves taking binary or exe files, depending on whether it's Windows or Linux. They can be converted into images as seen in this diagram. Once the images are converted, they are turned the 128 pixel images are turned into 14 by 14 images after they are encoded and after they are pre-processed using the quantum circuit. This sheds more light into my statement previously of how 128 into 128 images are being convolved into 14 by 14 images. Firstly, the design choice of using 4 qubits was that IBM, the most effective gate-based quantum computing provider, they have a free version which only has 5 to 7 qubits. So since we could solve our problem using only 4 qubits, we did not study the effectiveness of more qubits using a paid version of IBM. As we can see over here, the RY gates, which have a rotational angle of pi, are used to encode our image data of 128 into 128, and then they are passed into a complex circuit of quantum gates, where over here we use a rotational gate using the rotational values of pi by 4 each. The use of rotational gates was considered because they have edge detection properties, and using this particular circuit we found better, more edge refined processed images or processed values as shown in the diagram. In order to retrain the deep transfer learning model for the QCNN, we try to extract the feature extraction layer, the feature layer of a widely used deep transfer learning algorithm, and we perform small amounts of batch normalization and dropouts so that the overfitting issue is reduced. Additionally, as you can see in the DTL architecture, just like I previously mentioned, from data collection to data preprocessing, everything is being done before the feature extraction layer is implied and a fully connected layer is formulated. For the validation section, we try to provide a hybrid approach. We try to name our approach as a hybrid approach because we use a classical deep transfer learning algorithm which is assisted by quantum circuits and their feature extraction capabilities. For training, we use the Microsoft VS Code and the PennyLane software library for simulation because we ran multiple simulations, and using IBM's service would be very slow. So that's why we resort to PennyLane, which is a quantum circuit library which is 100% compatible with IBM. They have similar workflows, but the only difference is PennyLane simulates quantum circuits using mathematics, whereas IBM has actual quantum hardware. To train our algorithm, we use 1,000 samples of benign or good samples and 1,100 samples of malware. In order to test, we try to keep it as realistic as possible using 85 good samples and 8 malware samples because in a realistic system, maybe an inverter gets 100 updates every year, and out of those 100 update files, maybe 10 or 8 would be malicious. So that was the reason behind the unbalanced data set that we have. Lastly, over here we have the validation results between the classical uh, convolutional neural network and our hybrid quantum convolutional neural network. As you can see on the left, the classical CNN does not perform as good as the one on the right, which is the quantum CNN. And as you can see, we try to keep the deep transfer learning model same, just with the exception of using a quantum circuit and not using a quantum circuit. So as you can see, using a quantum circuit really decreases the amount of epochs we need to train our deep transfer learning network. Additionally, increases performance at least 10%. A more in detail comparison of the types of algorithms we have previously studied and we have analyzed during the publication of this paper. As we can see, the classical ResNet requires a lot of time when compared with the quantum variations, the quantum ResNet, the quantum dense net, and the quantum efficient net. The VGG16, the classical VGG16 reported over here is a previous research that we performed, which had very admirable amount of accuracy of 91% on our data set, which was a little different from the time this was implemented. But as we can see, since the VGG16 is such a large model and is such an accurate model, it takes a lot of training time, whereas our new contender, the quantum CNN ResNet 50 v2, only takes 500 seconds to train and has a very good accuracy with the precision of 1. In this paper, we really tried to find the best deep transfer learning method, which is being assisted by quantum circuits. And during that research, we really found out that the ResNet V version 250 had a better result because it had a precision of 1. In the case of malware, we can identify a goodware as a malware, that is acceptable, but identifying a malware as a goodware would be very dangerous for any system. That is what happens with the dense net and the efficient net. They don't have a precision of 1, whereas the ResNet 50 has a precision of 1. Using quantum assisted machine learning models can greatly increase accuracy and training time, as shown in this research. Other research areas may include the effectiveness of quantum machine learning against adversarial attacks. A lot of image based detection systems have been attacked and have a lot of research going on the types of adversarial machine learning attacks possible on CNNs. So the next version of this research would be to investigate how an adversarial attack can disrupt the decision of the machine learning model. Another scope would be to create a device specific CNN, which would be trained on multiple device specific files, so that regardless of the device, regardless of the OS of the device, we can efficiently detect malware in the system. This research was funded by the National Science Foundation under the award number as shown over here. And thank you for your time, and thank you for your support.